So first of all, let's remind ourselves what our isobaric or our constant pressure process looked like. We have our PV diagram. We have some constant pressure. It's not changing, P exterior. Whether we're going, whether we're expanding from V1 to V2 such that it's negative work, or if we go the other way and we compress between V1 and V2, doesn't matter. The area under this curve is the work being done. And by definition, we're always going to write the equation as work equals negative. This is also just a convention. Keep this here for our class alone. PdV, okay? Constant pressure over the change in volume. We can rewrite this as negative P exterior times V2 minus V1, okay? And the negative sign here makes this work out for us, right? We said that if we're going 2 minus 1, when it's expansion, 2 is bigger than 1, this would be a positive number. It'll be negative expansion work the way we want it. If we go the other way, such that we are compressing, so our V2 is actually the smaller number, this would be negative. Negative makes it positive. It's just to make everything work out the way we want it to. Okay? So this was our isobaric process. Enthalpy is defined by capital H. Okay? That's the notation that you'll probably see everywhere. I don't know that you'll have to worry about seeing anything weird. But it's also what we'll use here. So first of all, let's start by defining our first law of thermo, and we're going to rearrange some terms to get a definition of enthalpy. So change in internal energy is equal to heat plus work. We could also write it as, if we're going between two states, say state A to state B, then we could say the change in internal energy is the internal energy at state B minus the internal energy at state A. Okay. So then we would have Q. If I put a little subscript that's the letter P after heat, it's the notation to indicate constant pressure. Okay? So this is heat at constant pressure notation. So we've left Q alone here, and for work, we're going to go ahead and plug in our pressure volume relationship. Okay? So we've plugged in what we know work is equal to here, okay? Going from state A to state B. So then what we want to do is rearrange our equation. So we're just going to rearrange to get our heat on one side. So we'll have UB minus UA plus pressure times EB minus EA. Those are our volumes. Then I'm just going to multiply the pressure out. I'm going to multiply P through. So I have heat is equal to internal energy at B minus internal energy at A plus PVB minus PVA. And then I'm going to regroup things to get all the sort of A's and B's together. So constant pressure heat is equal to UB plus PVB minus UA plus P, this is a U, PA. This whole piece here is enthalpy at B. This whole piece here is enthalpy at A. Okay. So I could also say my constant pressure heat transfer is equal to enthalpy at B minus enthalpy at A, or is equal to change in enthalpy. Okay. I'll write that in words. Change in enthalpy is equal to heat transfer for a constant pressure process. And essentially, we defined, or someone, not me, defined enthalpy. I should probably know who it was. We'll just go with Boltzmann. He did a lot of stuff. That would be my official guess in some sort of trivia-based scenario, we defined enthalpy in order to have a state function, right, to relate to heat. We want to relate heat using only state functions. And so these are all state variables. We can take pressure at any given point. We can take volume at any given point. We can take internal energy at any given point. So H is equal to U plus, this is sort of a generic way to write the definition of enthalpy. Enthalpy is equal to internal energy plus pressure times volume. We are all state variables, which means I'm a state function. This is really important. The delta is key here. H does not equal Q ever. Again, there has to be heat can only be defined as a path, as a process between two things. I can't have heat of one state, A or B. But change in enthalpy is equal to QP. You could also see it like this. Heat's a path or process function. It's not a state function.